In this video, we're going to add to your math toolkit one of the most powerful tools that you'll ever have in dealing with quadratics. And that tool is called the quadratic formula. So to give you a bit of a overall idea of what it is, if you have a quadratic equation in this form of ax squared plus bx plus c. In other words, it's in standard form. And you'll notice that I've highlighted a and b in different colors to make them pop out, and c is in green as well for my standard form colors I've been using. You can find the roots of this parabola by using this equation. This equation looks pretty funky. You can actually see the derivation of where it comes from on page 293 of your textbook if you're interested. But it reads as follows. It reads the value of x for the roots of that particular relation is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And there's a piece of this equation that has a very special name, this piece that is underneath the square root, or the radical we call it. This is called the discriminant, and we'll learn in this lesson the importance of the value of that discriminant in learning about some properties of a given parabola. So let's begin by looking at how we can find the roots of a particular relation. And we're going to look at an example where we have something called two rational roots, and I'll show you what I mean by that as well. So in this example, we are asked to solve the equation 3x squared plus 5x minus 2, and of course it's equal to 0, and we're solving for it in two ways. First way is, can we do it by factoring it? And the other way is, could we solve for it using our new equation, our new quadratic formula? I'm going to call it QF for short. So let's try factoring first. I realized that in order to factor this, there is no GCF for starters. So next I look at, is it a perfect square trinomial? And the answer is no, it's not. So then I say, well, I need two numbers that multiply to give a times c and add to give b. So your little thinking table that we learned about in chapter 5. Two numbers that multiply give negative 6 and add to give 5. Well, when it comes to getting negative 6, we can have 1 and 6. We would allow the smaller one to be negative here, so that when they're added together, we get a positive 5 result, and there you go. So if we're going to factor it this way, we can use the Berry method, or we can use split the middle term. If you want to this time, because in previous lessons I've been doing split the middle term, here I'll do Berry instead. So I intentionally write 3x and 3x at the beginning of each binomial, and then I choose to use each of these in each spot. Now remember, when I did 3x and 3x here, I intentionally have an extra factor of 3 that's going to have to come out of the answer, because of course 3x times 3x does not equal 3x squared equals 9x squared. There is an extra factor of 3, so that's a little star to remember to do that. So what I do then, if I'm using the Berry method, is I take out the GCF for each of these. Now the first binomial does not have a GCF, but the second one does. It has a GCF of 3, which leaves me with x plus 2. Now remember how I said we need to eliminate that extra factor of 3? There it is. And so my answer, factored, would be 3x minus 1 times x plus 2. And if you did the split the middle term method, you should get the exact same answer. So if we want to find the roots, because of course both of these are equal to 0, I can let 3x minus 1 be 0, but I can also let x plus 2 be 0, so that this equation is true. Rearranging for x gives me 3x equals 1. Dividing both sides by 3 gives me x is a third. On this side, subtracting 2 from both sides will yield me a value of x equals negative 2. So there are the two roots of this particular parabola. Let's try this time solving it using our new quadratic formula. So I'm going to replace a, b, and c with their colors, just so that you can start to see how the quadratic formula works in terms of subbing in properly. So my a value is red, my b value is orange, and I'm letting my c value be green. And I should include a color with each of the signs as well, so that remember that the signs have to be subbed in too. So the quadratic formula is the value of x for the roots is equal to negative b. So negative positive 5 will just become negative 5. But I'm going to actually show you explicitly how to sub it in. There, I'm going to put that in for b. I'm going to go plus or minus. I'll show you what that's all about in a little bit. B squared. So b squared, if you want, just you could do it in your head. 5 times 5 is 25. Minus 4 times a. A has a value of 3. Times c. C has a value of negative 2. And all of that is divided by 2 times a, or in this case, 2 times 3. So I'm going to remove the colors now that you can see how the substitution process worked. And let's see if we can simplify this. So x is equal to negative 5 plus or minus the square root of 25. And then all of these are being multiplied by each other. So negative 4 times 3 times negative 2. Well, this is negative 12 times negative 2 is plus 24. And that all gets divided by 6. So let's keep going. Plus or minus the square root of 49 over 6. Well, we know what the square root of 49 is. It's 7. So what this plus minus means is that there are two possible answers. There's an answer we can get for x where we use the positive value, and also a value of x where we use the negative value, or negative 7 instead. So I'm going to show you what each of those look like. Let's do the positive one first over here and the negative one over here. So x would be equal to negative 5 plus 7 over 6, which is 2 over 6, which comes out to 1/3. And if I use negative 7 instead, I'm going to have x is going to be equal to negative 5 minus 7 over 6, which is going to be negative 12 over 6, which is equal to negative 2. Well, look at that. We got the exact same answers for the roots using the quadratic formula or factoring. Now you can see clearly that if you can factor to get the roots, it's an awful lot shorter than having to use the quadratic formula. So you might ask, well, why would anybody use the quadratic formula? Well, let's look at another example to see if we can answer that exact question. In example 2, we're going to show you that the roots come out as being something called irrational. So we begin in example 2 with a quadratic relation that says x squared minus 3x equals negative 1. And we are asked to solve. And again, solving means finding the roots or finding the x-intercepts. And we're asked to express the answers exactly and also as approximate roots. So what I'd like to do with this is I'd like to see if I could factor it first. And so what I'm going to do is I'm going to arrange it so that all of the terms are on one side and I'm equal to 0, and then I can look at this critically and say, is it factorable? Well, if I go through my factoring ideas, first I look for a greatest common factor, and there isn't one. And then because it's a trinomial decreasing powers of x, I might say, is this a perfect square trinomial? This is a perfect square and this is a perfect square, but this is not equal to double the root of that times the root of that. So this is not a perfect square trinomial. So your next step would be, are there two numbers that multiply to give a times c, which is 1, and add to give negative 3? Now right here is where you realize that this is not easily factorable, because the only two numbers that multiply to give 1 are 1 and 1. And there's no way they're going to add to give negative 3. So sadly for us, factoring is not possible. Factoring is a sad face. You're like, oh, that's really too bad. I love factoring. I'm like, wow, lucky for you now, we have plan B. We can't factor, so instead we're going to use the quadratic formula to solve for those roots instead. So let's be explicit while we're learning how to use it. Our A value is equal to, right here, a 1. Our B value in standard form here is negative 3. And our C value right here is equal to 1. And sometimes while you're learning, it's nice just to put those out there so that you can make the substitution easier without any crazy little negative errors. So let's find these roots. So x, and I'm not going to bother putting the roots here anymore because as soon as we use this equation, we know that we're trying to find the roots, is equal to negative b. So what is the opposite of negative 3? It's positive 3. That's really what this step is doing. Plus or minus the square root of b squared. Can you do negative 3 times negative 3? Yes, in your head you can just say, I'm going to put a 9 in there. Notice that this term here will always end up being positive because a positive value squared is positive and a negative value squared is also positive. Okay? Minus 4 times a, which is 1, and c, which is 1. And all of this is divided by 2 times a, and a is equal to 1. Let's simplify. It's equal to 3 plus or minus the square root of 9 minus 4 times 1 times 1. Well, that's going to be 9 minus 4, or root 5, divided by 2 times 1, which is 2. So I've ended up with a discriminant value here of 5 that is not a perfect square root. And so when a question asks you for the exact roots, this is where you would leave it. You would stop right there. The exact roots mean leaving it in radical form. I'm going to write that in here. Because, again, this is not a perfect square. So why make it into some sort of decimal that goes on and then truncate it or cut it off and say that's accurate? So the exact roots would be, if we do the positive version and the negative version, we would have x is 3 plus root 5 over 2, and we would have x equals 3 minus root 5 over 2. Okay, so again, these are the exact roots right here, if you want to be explicit. Now, if we want to do approximate roots to the nearest hundredth, then we would punch each of these into our calculator. Now, it's super important when you do that to make sure that when you punch in 3 plus root 5 that you hit equals and you get that sum before you divide by 2, and in a similar way that you do 3 minus root 5, you get that difference, you hit equals before you divide by 2. So you will get a decimal answer, okay? And if I punch these into my calculator, 3 plus root 5 equals, divided by 2, I get x being approximately equal to 2.62 if I round to the nearest hundredth. Okay, and you'll have to watch on questions whether you're being asked to round to the nearest tenth, which is the first decimal place, or to the hundredth. My calculator actually says 2.618, and so that's how I knew to round it up to 2. I'm going to do the similar thing, but I'm going to subtract root 5 from 3 instead. So 3 minus root 5, hit equals, divide by 2, and you get a decimal of 0.3, and then it says 81. So since the digit after the 8 is less than 5, I'm going to leave it as 8. And these are your roots. These are your x-intercepts. So the quadratic formula is powerful because it works for all roots, whether they are in fact integer values or whether they're decimals. Integer values are more easily found usually through factoring, but that doesn't represent the majority of parabolas in everyday life. So this is a powerful tool. All right, let's look at another example. This time we're going to look at what happens if a parabola only has one root, because so far the two examples we've done have two roots. They have two x-intercepts. They cross twice. But we know it's possible for a parabola's vertex to touch the x-axis, and therefore there will only be one root as well. So in example 3, one root. I'm going to give you the equation 4x squared minus 20x plus 25 and ask you to solve it. Again, solving is finding the roots, so we want to make sure that all the terms are together and we have equals 0 on the other side, because this means y equals 0, which is the condition of x-intercepts. So if you can, the first thing you want to try and do is factor it. So let's try factoring it. We look for a greatest common factor, and there isn't one for all three terms. Then we ask ourselves, is this a perfect square trinomial? Well, let's do the 3-point test. 4x squared is a perfect square. Okay, it can be square rooted to give 2x. 25 has a perfect square of either 5 or negative 5. And negative 20x is equal to 2x times 5 and doubled, right? And it's going to be 2x times negative 5 and doubled because it's negative. So if it is a perfect square trinomial, it means that it is equal to a binomial times itself. And we practiced this when we did completing the square. So this goes down to 2x for the square root of this, 5 for the square root of this, and negative because of the sign of b. Okay. So, I mean, what this really means, as you know, is a binomial times itself, but we don't need to set both of those equal to 0 separately because we know they're going to have the same answer. So if I say 2x minus 5 is 0, I can then solve for x by adding 5 to both sides and then dividing both sides by 2 to get 5 halves. So there's only one root. Okay? It means that if we're sort of sketching this, this parabola is just, it's upward, I know that by its a value, and it's just touching the x-axis at 5 halves. Okay? It's only got one root, or one x-intercept. We could also solve it using the quadratic formula. So let's see this time if you can pull A, B, and C, and you got to make sure that they're in decreasing order, power of x, by the way, before you say this is A, this is B, this is C. If they're out of order, you have to look for A being the coefficient of the x squared term, B being the coefficient of the x term, and C being the numerical value that has no literal coefficient. That's really important. Okay, so x is equal to negative b. B here is negative 20. Maybe what I'll do is I'll just do a color thing here. So the negative of that would be positive 20. Plus or minus the square root of b squared. Well, negative 20 times itself would be 400. Minus 4 times a. A is the value in front of the x squared term. It's a 4. Times c, which again is that term that has no literal coefficient. Times 25, all over 2 times a, and again a is 4. So let's simplify this. X equals 20 plus or minus the square root of 400 minus 4 times 4 times 25. Well, I know 4 times 25 is 100, times 4 is 400, all over 8. Well, look what happens here. We end up with 400 minus 400, or the square root of 0. So there is no 20 plus the square root of 0 and 20 minus the square root of 0 difference, because the square root of 0 is 0 no matter what. So we only have one root. We have 20 over 8, which can be reduced down if we divide both of them by 4 to 5 halves. And this is not surprising because we found it using the factoring method too. So there's only one root. So isn't it interesting that when the discriminant goes to a value of 0, we end up with one root. When it was a positive value, we ended up with 2 roots. So this leads us very nicely into one more example. What happens if we have no roots? What's that going to look like when we use the quadratic formula? So for example 4, no real roots. We have the equation x squared plus 4x plus 7 equals 0, and we're asked to solve it. In other words, find out where its x-intercepts are. So again, if you can factor it, you want to do that first. It has no GCF. It's not a perfect square trinomial, so I need two numbers that multiply to give 1 times 7 and add to give 4. Well, there are only two numbers that multiply to give 1 times 7, or to multiply to give 7. That is 1 and 7, and there's no way they're going to add to give 4. So factoring is out. So we're going to have to try using the quadratic formula. So x equals negative b. There's our b value, so negative 4, plus or minus the square root of b squared. 4 times 4 is 16, minus 4 times a has a value of 1 times c, which has a value of 7, all over 2 times a, which again is 1. Let's simplify this and see what happens. We end up with 16 minus, well, 4 times 1 times 7 is 28, all over 21. Or sorry, 2. There we go. So x equals negative 4 times the square root of negative 12 over 2. And I forgot the plus or minus in here. Sorry about that. There we go. So guess what happens when you try and find the square root of 2? Or sorry, square root of negative 12. So square root of negative 12. Your calculator says, that's not possible. But that makes sense, because what number do you know of that you can multiply by itself or square it and get a negative value? You can't. So the discriminant here is impossible to solve, which therefore means there's no real roots. Now if you put this into Desmos, what you'll discover is you're going to end up with a parabola that's upward facing, of course, okay, but it's going to end up being above the x-axis. So it makes sense that there's no roots because it doesn't cross the x-axis anywhere. So let's go back quickly and recap what we learned in terms of the importance of the discriminant in connecting to the number of roots. Okay, so if you have the discriminant being bigger than 0, okay, I'm just going to call it D for the discriminant. If it's bigger than 0, what we're saying is it's a positive value. Okay, so in other words, this piece here, b squared minus 4ac, taking off the square root form, just looking at this piece, has to be bigger than 0. If that happens, we end up having 2 roots, meaning that the parabola crosses twice. So, I mean, you can have all kinds of scenarios. You can have a parabola that crosses the x-axis twice, one on either side of the y, or maybe it crosses on both sides of the y, or maybe both sides, or sorry, on the right side of the y over here, or on the left side of the y here, up, down, shifted high, low, skinny, wider, doesn't matter. Okay, there's a whole bunch of scenarios. If you end up with the discriminant being equal to 0, we discovered that you have 1 root. And so what that means is that your parabola is just touching the x-axis somewhere. It even might be centered on the y-axis, but it might not be. It could be shifted left, it could be shifted right. It could be wider, it could be narrower. Okay? But the whole point is that the vertex and the x-intercept are one and the same thing. That's pretty cool. And then finally, if our discriminant is less than 0, in other words, if it is negative, we discover that there are no roots. Kind of like that song, you know, got no roots, da 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 da. You know what I mean? So, you know, lots of scenarios for that. Maybe you have an upward facing one that is above the x-axis. Or you have a downward facing one that is below the x-axis. Okay, no roots because it doesn't cross. So this discriminant is a really great tool, especially when you're given the equation for a quadratic in standard form. I'll stop this video here and pick up the next one with some more examples for this lesson.